The sound of a winter night on the high plains is rarely silent. It is a discordant, metallic shriek. When the mercury drops to -40 degrees Fahrenheit, the very molecules of a galvanized steel structure begin to crawl. The metal moans, a high-frequency vibration known to those who live in the wind-swept barrens as the Quonset cry. It is the sound of a building trying to shrink away from the cold. Outside, the wind is a solid wall of 60-mile-per-hour kinetic energy, carrying with it a blinding slurry of crystalline ice. It should be a death trap. Conventional survival wisdom dictates that a thin-skinned steel shell in these conditions is nothing more than a galvanized coffin, a high-efficiency refrigerator designed to strip the life from anything trapped inside. Now, picture this. Inside that very same steel shell, the air is a steady, unmoving 70 degrees. There is no roar of a forced air furnace. There is no frantic stoking of a wood-burning stove. The interior is a sanctuary of unnatural stillness, while the world outside is being erased by a whiteout. If you were to step outside and look through the swirling chaos, you wouldn't even see the building. You would see a jagged, skeletal forest of dried sunflower stalks, lignified, brown, and rattling like the bones of giants, standing 10 feet tall in a staggered grid. These are not the bright yellow blooms of summer. They are the desiccated structural remains of Helianthus annuus, and they are currently performing a miracle of fluid dynamics. Here's what everyone missed. The secret to surviving a 72-hour blizzard in a military surplus hut isn't found in the thickness of the steel or the complexity of the heater. It's found in the drag coefficient of a dead flower head. The numbers don't lie. While the wind screams against the stalks, a low-pressure zone is forming a snow shadow that is systematically burying the hut in a calculated blanket of white. By the time this storm ends, the metal won't be exposed to the wind at all. It will be encased in an atmospheric armor of packed snow, one of the most effective natural insulators on the planet. But before we can understand how this botanical shield works, we have to understand the fundamental failure of the machine it was designed to protect. We have to look at why. For over 80 years, the Quonset Hut has been both a triumph of industrial logistics and a thermodynamic nightmare. If you find this deep dive into the mechanics of extreme survival valuable, consider subscribing. It ensures we can keep providing these unabridged engineering breakdowns. To understand the danger of the steel hut, we must go back to 1941 to a place called Quonset Point, Rhode Island. The United States military was on the brink of a global conflict and needed a structure that could be shipped in crates and assembled by unskilled laborers in less than a day. They looked across the Atlantic to the British Nissen hut, a semi-cylindrical design from the First World War, and they refined it for the American industrial machine. They used corrugated galvanized steel, a material prized for its durability and resistance to the elements, but a material that possesses a hidden, lethal flaw when the temperature drops. By the end of World War II, the production lines had churned out more than 150,000 of these units. When the war ended, the government didn't know what to do with them. They flooded the civilian market, selling them as surplus for as little as $1,000. For thousands of returning veterans and rural families, it looked like the American dream in a crate. It was a cheap, fireproof, and rot-proof home that could be bolted together on a concrete slab in a weekend. But as these families moved into the Great Plains and the Northern Territories, they discovered the physics of their new homes was working against them. Think about that for a second. You are living inside a material with a thermal conductivity of roughly 50 watts per meter Kelvin. To put that in perspective, galvanized steel is nearly 400 times more conductive than the wood used in a traditional cabin. In the world of thermodynamics, steel is not a wall. It is a highway. It is a high-speed conduit designed to move energy from where it is to where it isn't. When the wind hits the exterior of a bare Quonset hut, the steel doesn't just get cold. It actively sucks the infrared energy out of the room and pumps it into the atmosphere. Let that sink in. If your heat source fails in a standard, uninsulated Quonset hut during a northern winter, the interior temperature will reach the ambient outdoor temperature in less than 90 minutes. It is the ice cube analogy in reverse. Just as a metal tray pulls heat out of water to create ice, the steel ribs of the hut pull the warmth out of your lungs. This is known as thermal bridging. Every single steel bolt, every corrugated rib, and every floor joist acts as a bridge for the cold to cross. In many of these surplus homes in the late 1940s, families would wake up to find a thick layer of white frost on the interior of the walls, directly mimicking the pattern of the ribs outside. They were living inside a radiator that was radiating cold. The tragedy of the 1949 Great Plains blizzard highlighted this engineering gap with brutal clarity. It was one of the most severe winters in recorded history, with snowdrifts reaching the tops of telephone poles and temperatures hovering at 30 below zero for weeks. Rescue crews found families frozen in their Quonset huts, even though they still had wood for their stoves and oil for their lamps. The problem wasn't a lack of heat, it was the inability to retain it. The wind chill was so aggressive that it stripped the heat from the outer shell faster than any stove could replenish it. But there was a second, more insidious killer, lurking in the design, the air itself. Because the Quonset hut is essentially a giant, airtight metal tube, once the seams are caulked, it creates a vacuum effect. In 1949, as the snow piled up against the sides of these huts, it blocked the low-level vents. People inside, desperate for warmth, would crank their wood stoves to the maximum. But a fire is a living thing. It needs oxygen to breathe. Without a dedicated external air intake, a feature almost entirely missing from the original 1941 blueprints, the stove would begin to consume the oxygen inside the living space. As the oxygen levels dropped, the combustion in the stove became incomplete, and the byproduct changed from harmless carbon dioxide to lethal carbon monoxide. Because the snow had buried the structure, the chimney, often just a short pipe sticking out of the curved roof, would become shrouded in a pocket of stagnant air, or, worse, buried entirely. The carbon monoxide, unable to escape against the pressure of the wind and snow, would backdraft into the cabin. It was a silent, odorless executioner. The very tightness of the steel construction, which was supposed to keep the elements out, ended up trapping the poison in. The survivors of those early winters learned quickly that the Quonset hut was a paradox. It was strong enough to withstand the weight of a foot of snow, but it was thermodynamically leaky. The steel ribs were structural masterpieces, capable of distributing the load of a blizzard across their entire arcuate frame, yet they were failures as a thermal envelope. The corrugated surface area, which gave the thin metal its incredible rigidity, also increased the surface area exposed to the wind, effectively turning the entire house into a giant heat exchanger. To fix it, you couldn't just add more fire. You had to change the relationship between the building and the wind. You had to find a way to stop the air from touching the steel altogether. You needed a barrier that wasn't made of expensive, heavy materials that would crush the frame, but something light, something renewable, and something with the structural integrity to stand up to a gale. This is where the unconventional logic of the sunflower enters the record. We are looking at a plant that has evolved for millions of years to stand tall in the wide-open prairies, using a lignified cellular structure that rivals the strength-to-weight ratio of engineered timber. When you look at a dried sunflower stalk in December, you are looking at a masterpiece of natural carbon fiber engineering. The outer skin is a hard, siliceous rind, while the interior is a localized pith that provides incredible flexibility. In the 1950s, a handful of off-grid pioneers and agricultural researchers began to notice something about the way snow drifted around these stalks in the fields. While the rest of the prairie was scoured clean by the wind, the areas behind the sunflower patches were deep, calm reservoirs of snow. They realized that if you could harness that snow shadow, you could turn the very blizzard that was trying to kill you into the insulation that would save you. But the physics of this living windbreak is incredibly precise. You cannot simply plant a row of flowers and hope for the best. If the stalks are too close together, they act as a solid wall, and the wind will simply ramp over them, creating a vortex that can actually rip the roof off a structure. If they are too far apart, the wind accelerates between them, a phenomenon known as the Venturi effect, turning each gap into a high-pressure nozzle of ice and grit that can sandblast the paint right off the galvanized steel. To make a Quonset hut survivable, you have to master the drag coefficient of the Helianthus. You have to understand how to turn a flower into a mechanical buffer, and that is where the true audit of this survival strategy begins. To move from a state of vulnerability to one of biological fortification, we have to look closely at the architecture of the Helianthus annuus, the common giant sunflower. In the height of a lush July, these plants are celebrated for their vibrant yellow petals and their uncanny ability to track the sun across the sky. But for the survivalist in the high desert or the wind-scoured plains, the beauty of the flower is a secondary concern. The real value lies in the plant's senescence, its transition into a skeletal, lignified state as the autumn frost kills the internal tissues. This is where the engineering begins. The sunflower is not a soft-stemmed herb. It is a carbon-sequestering machine that produces a stalk with a strength-to-weight ratio that rivals many softwoods. As the plant matures, it undergoes a process called lignification. The cell walls are reinforced with lignin, a complex organic polymer that acts as a natural resin, turning a flexible green shoot into a rigid, hollow core pillar. By the time the first blizzard of November rolls across the horizon, these stalks have become as hard as bamboo. If you were to take a machete to one of these dried stems, you would not hear a wet thud. You would hear the sharp, resonant clack of wood. This structural rigidity is the first requirement for our living windbreak. It has to withstand lateral wind loads of 60 miles per hour without snapping at the base. To achieve this, the soil must be rich in silica and potassium, minerals that the sunflower voraciously mines from the earth to reinforce its siliceous rind, the hard, glass-like outer skin that protects the pithy core. Now, imagine the layout. We are not planting a garden. We are constructing a fluid, dynamic baffle system. The engineering of the living windbreak requires a staggered grid, a pattern often referred to in classical architecture as a quincunx. To the untrained eye, it looks like a dense thicket, but to a physicist, it is a calculated arrangement designed to disrupt laminar flow. We plant 3 distinct rows of sunflowers in a concentric arc around the windward side of the Quonset hut, typically focusing on the northwest quadrant where the most lethal winter gales originate. The spacing is critical. Each stalk is positioned exactly 24 inches from its neighbor, and each row is offset by 12 inches to close the windows between the stems. Think about the physics of the wind as it approaches this barrier. In an open field, the wind moves in a laminar fashion, smooth, fast, and unobstructed. When it hits a solid wall, like the side of a steel hut, it creates a high-pressure zone on the face and a violent low-pressure vacuum on the roof, which can literally suck the heat out of the building through every microscopic seam. But when that same wind hits our staggered grid of sunflower stalks, it is forced to deviate. It cannot move in a straight line. It is broken into 1,000 smaller currents, spinning off into turbulent eddies. This is where we exploit the Reynolds number, the mathematical ratio that describes the transition from smooth to chaotic fluid flow. By forcing the wind to become turbulent, we are stripping it of its kinetic energy before it ever reaches the galvanized steel of the cabin. But the stalks are only half of the equation. The true genius of this botanical shield lies in the dinner plate, the massive, dried seed head that remains atop the 10-foot stalk. In the summer, these heads are heavy with moisture and seeds, often drooping under their own weight. But as they dry, they become incredibly light and remarkably stiff. Each head, measuring between 12 and 18 inches in diameter, acts as a drag-inducing baffle. When you have thousands of these heads rattling in the wind at a height of 10 feet, they create a high-altitude drag zone. Here is the mechanical audit of that effect. The wind hits the top of the sunflower forest and is forced to slow down. This creates a low-pressure zone immediately behind the stalks, extending toward the hut. This is what we call the snow shadow. In the world of fluid dynamics, when wind velocity drops, the air loses its carrying capacity. The snow, which was being whipped along at 60 miles per hour, suddenly loses its lift. It falls out of the air, like lead. Instead of the snow being blasted against the steel ribs of the hut, it begins to settle in the calm air created by the sunflowers. This is a deliberate, step-by-step accumulation. The first row of sunflowers catches the initial brunt of the blizzard, causing the first massive drift to form several feet away from the structure. As that drift grows, it alters the local topography, creating a ramp that further slows the wind. The second and third rows of sunflowers continue this process, trapping the snow in the valleys between the rows. Within 6 hours of a major storm, the area between the sunflowers and the Quonset hut is no longer a wind tunnel, it is a reservoir. The snow begins to pile up against the curved sides of the hut, not with the force of a hammer, but with the gentleness of a falling blanket. Let us look at the structural loads involved here. A standard Quonset hut, with its corrugated 19-gauge steel, is designed to handle significant vertical pressure, the weight of snow sitting on top of the ark. However, it is much more vulnerable to lateral pressure, the force of wind pushing against the side. By using the sunflowers to create a snow shadow, we are essentially converting a high-velocity wind load into a static snow load. While 20 pounds per square foot of snow might sound like a lot, the arcuate shape of the hut is perfectly engineered to distribute that weight down through the ribs and into the concrete foundation or the timber skids. The steel doesn't buckle, it settles. The engineering of the grid also prevents the Venturi effect. If we had planted these stalks only 6 inches apart, we would have created a series of high-pressure nozzles. The wind would have compressed as it moved through the narrow gaps, actually increasing in speed and creating a sandblasting effect that could strip the galvanized coating right off the steel. By maintaining the 24-inch spacing, we ensure that the wind is slowed and diffused rather than compressed and accelerated. It is a delicate balance of porosity. The shield must be leaky enough to let the air pass through, but dense enough to break the wind's coherent structure. As the blizzard reaches its 12-hour mark, the snow shadow has done its job. The Quonset hut is now being encased in a layer of snow that is growing at a rate of several inches per hour. This is where we see the transition from mechanical protection to thermodynamic insulation. But to make this work, the builder must have planned for the thermal mass isolation of the structure itself. You cannot simply bury a steel hut and expect it to stay warm if the floor is sitting on frozen dirt. The step-by-step engineering of the foundation is just as critical as the sunflowers. Before the hut is even bolted together, a thermal break must be established. This usually involves a floating floor design. We start with a bed of compacted gravel for drainage, followed by a layer of high-density extruded polystyrene foam at least 4 inches thick, which acts as the primary barrier between the steel and the earth. On top of this, we lay a subfloor of 3/4-inch marine-grade plywood. But the real secret to thermal mass isolation in this specific sunflower protocol is the use of the internal furring strip. Remember, galvanized steel has a thermal conductivity of 50 watts per meter Kelvin. If you bolt your interior plywood walls directly to the steel ribs, you have created a thermal bridge. The cold will simply travel through the bolt and into your living space. To prevent this, every rib of the Quonset hut is lined with a 1 by 3 inch cedar furring strip. Wood has a thermal conductivity of only 0.12 watts per meter Kelvin. By placing this thin strip of cedar between the steel and the interior wall, we have effectively cut the highway for the cold. We have created a thermal air gap that prevents the frost line from ever touching the interior cladding. Now, picture the scene as the storm reaches its peak at the 24-hour mark. The wind outside is a screaming void of white, but the sunflowers are standing their ground. The lignified stalks are swaying, bending under the pressure, but their circular cross-section and siliceous rind allow them to flex without snapping. They are like a forest of tiny, natural springs. Every time a stalk bends, it absorbs some of the wind's energy. Every time it snaps back, it sheds the ice that has attempted to accumulate on its surface. Behind this rattling skeletal wall, the Quonset hut is disappearing. The snow has reached the 5-foot mark halfway up the curve of the steel walls. Inside, the temperature is actually beginning to rise, even though the fire in the stove has been banked for the night. This is because the snow being deposited by the sunflower shield is not just weight. It is an atmospheric armor, Freshly fallen, wind-packed snow has an R value of approximately 1 per inch. By the time the sunflowers have helped trap 60 inches of snow against the hut, we have created an R60 insulation blanket around the entire structure. Let that sink in for a moment. A standard, modern home in the United States is required to have an R value of about R38 in the attic. We have nearly doubled that, using nothing but the byproduct of a summer crop and the kinetic energy of the blizzard itself. The steel shell of the Quonset Hut, which was once a refrigerator, has now become the interior lining of a massive, high-efficiency igloo. The thermal bridging has been neutralized because the exterior temperature of the steel is no longer minus 40 degrees. It is being held at a relatively warm 32 degrees by the insulating snow. But this engineering feat brings with it a lethal new variable that every builder must account for: the seal of the snow. As the sunflowers facilitate the burial of the hut, they are also sealing off the natural air infiltration points. A Quonset hut is a semi-cylindrical pressure vessel. In a normal environment, air leaks in through the door seals and the base plates. But when you are encased in 5 feet of packed snow, those leaks vanish. The cabin becomes nearly airtight. This is where the external combustion air intake becomes a mandatory part of the engineering blueprint. You cannot rely on room air to feed your heat source. If you are burning a wood stove or a propane heater inside a buried Quonset hut, that fire is consuming liters of oxygen every minute. In an airtight space, it will create a negative pressure environment. The stove will begin to gasp, struggling to find air. Eventually, it will pull air down from the chimney, the very place where the smoke and carbon monoxide are supposed to be exiting. To solve this, a 2-inch diameter pipe, typically made of heavy-duty steel or high-temp PVC, must be run through the floor, directly under the stove's intake vent. This pipe extends through the foundation and exits 20 feet away from the building, well beyond the snow shadow created by the sunflowers. This ensures that the fire has its own dedicated lung, drawing fresh, oxygen-rich air from the outside without ever touching the oxygen inside the cabin. It is a simple piece of plumbing, but in the context of the 72-hour survival log, it is the difference between waking up in a warm room and never waking up at all. As we move into the second day of the blizzard, the living windbreak has undergone a transformation. The sunflowers are no longer visible as individual plants. They have been subsumed into a massive, jagged drift that looks like a natural ridge in the landscape. This ridge is the deflector. It is now so large that it is pushing the wind up and over the hut entirely. The aerodynamic profile of the structure has been changed from a blunt object to a teardrop shape. The wind velocity at the actual surface of the hut, or what's left of the exposed roof, is now less than 10% of the ambient wind speed. The precision of the 24-inch grid is now being tested by the whump factor. This is the sound of the snow settling. As the weight of the drift increases, the air is squeezed out of the lower layers of snow, turning it from soft powder into a dense, structural material. If the sunflowers were planted in a straight, non-staggered line, the snow would have settled unevenly, potentially creating an unbalanced load on the Quonset ribs. But because of the quincunx pattern, the snow has been deposited in a uniform buttress around the circumference of the hut. The pressure is equalized. The steel ribs are being squeezed from all sides simultaneously, which is the state in which a cylinder is strongest. Inside the cabin, the sensory experience is profound. The metallic shriek of the contracting steel that we heard at the beginning of the storm has been replaced by a heavy, muffled silence. It is the silence of the earth. The thousands of tons of snow resting against the sunflowers and the hut are not just blocking the wind, they are blocking all sound. The only thing the occupant hears is the soft crackle of the wood stove and the steady tick-tick-tick of the heat, expanding the interior cedar cladding. We have achieved thermal mass isolation. The temperature inside has stabilized at 72 degrees Fahrenheit, and it requires only a single small log every 2 hours to maintain it. The refrigerator has been defeated by a combination of 1940s military surplus and a botanical barrier. But we must not forget the most critical engineering component of the roof, the snorkel chimney. In a standard Quonset installation, the chimney pipe might only extend 24 inches above the peak of the arc. In a sunflower shield scenario, That is a fatal mistake. As the snow shadow grows, the drift can easily exceed 6 feet in height, especially near the center of the arc where the wind eddies. If the chimney is buried, the carbon monoxide has nowhere to go. It will find the path of least resistance, which is back through the stove doors and into your lungs. The snorkel extension is a 4-foot section of double-walled insulated pipe that is bolted to the main flue. It is braced with 3 galvanized steel cables anchored to the ribs of the hut to prevent it from being snapped off by the sheer weight of the wind-driven snow. This extension ensures that the exhaust termination point remains at least 24 inches above the highest anticipated snowdrift. It is the periscope of the survival cabin, the only part of the structure that still communicates with the violent world outside. As we audit the mechanics of this system, we see that it is a passive-active hybrid. The sunflowers are passive, they grow with nothing but sunlight and rain. The snow is passive, it is provided by the storm. But the engineering required to coordinate these elements is highly active. It requires an understanding of botany, thermodynamics, and fluid dynamics. It is the antithesis of the high-tech survival solution that relies on backup generators and complex electronics. It is a solution that uses the very elements of the disaster to provide the protection. Think about the sheer elegance of the lignified stalk one more time. In the spring, these plants will be pulled from the ground and composted, their minerals returning to the soil to grow the next year's shield. They are a renewable, carbon-neutral engineering material that performs a task most modern fences cannot. They don't just stop the wind, they negotiate with it. They use the wind's own energy to build a wall of snow. This is the living windbreak in its final form, a masterpiece of unconventional construction. But the 72-hour mark is approaching, and the storm is reaching its terminal phase. The weight of the snow is at its maximum. The oxygen levels are being monitored, and the snorkel is being tested by a final, desperate surge of the Great Plains wind. We are about to see if the physics of the dead flower can truly hold up against the physics of the ice. The numbers don't lie. At this point in the 1949 blizzard, many Quonset huts were already failing. But here, inside the sunflower shield, the air remains still, the steel remains warm, and the occupant is no longer a victim of the elements. They are a resident of a climate-controlled sanctuary, buried deep beneath the white chaos of the prairie. We have successfully turned a galvanized coffin into a fortress of stillness, and the step-by-step engineering of that transformation is a blueprint for survival that everyone missed until now. As the snow begins to consolidate against the corrugated flanks of the hut, we move from the realm of fluid dynamics into the realm of pure thermodynamics. This is the moment where the snow shadow transitions into a thermal battery. To understand why this works, we have to look at the microscopic structure of a snowflake. A single snowflake is a complex, branched lattice of ice crystals that traps an incredible amount of air within its geometry. When the wind slowed by our grid of lignified sunflower stalks deposits this snow in a dense, uniform layer against the galvanized steel, it is essentially applying a layer of natural fiberglass insulation. Think about that for a second. The thermal conductivity of air is incredibly low, roughly 0.024 watts per meter Kelvin. By trapping that air within the snow lattice, we create a substance with an R value of approximately 1 per inch. While a single inch of snow might not seem like much, remember the sunflower shield is engineered to create a drift that can easily exceed 60 inches in depth. When you multiply that R value across the 5-foot thick buttress of snow leaning against the hut, you are looking at an insulation barrier of R60. The numbers don't lie. At minus 30 degrees Fahrenheit, a bare steel wall is a thermodynamic catastrophe, but a steel wall buried under 5 feet of packed snow is a different machine entirely. The exterior surface of the metal is no longer exposed to the 40-mile-per-hour wind chill that strips heat away via convection. Instead, it is touching a static layer of snow that is being held at a constant 32 degrees Fahrenheit by the latent heat of the earth and the interior heat of the cabin. We have effectively moved the thermal gradient, the line where the heat meets the cold from the thin skin of the steel to the outer edge of the snowdrift, 3 feet away from the building. But this natural igloo effect creates a secondary engineering challenge that is often fatal to the unprepared. We must discuss the physics of the oxygen deficit. In a standard, drafty wooden cabin, air enters through 1,000 tiny cracks in the window frames and floorboards. But a Quonset hut, by its very design as a military-grade pressure vessel, is remarkably tight once the seams are caulked. When the snow shadow buries the hut, it acts as a hermetic seal. Every point of natural air infiltration is suddenly blocked by a wall of dense, ice-packed crystals. Now, picture this. You are inside, feeling warm and secure. Your wood stove is roaring, and the temperature is a comfortable 70 degrees. But that fire is a chemical reaction that requires a massive volume of oxygen to sustain itself. For every kilogram of wood you burn, the stove consumes roughly 10 cubic meters of air. In an airtight, snow-buried environment, the stove will quickly deplete the oxygen in the living space. As the oxygen levels drop from the standard 21% toward 16%, the combustion process begins to fail. This is where the engineering of the external combustion air intake becomes the most critical component of the blueprint. We do not pull air from the room. Instead, we have installed a dedicated 3-inch diameter steel pipe that runs from the base of the wood stove directly through the floor and out to the exterior foundation. This pipe acts as a direct umbilical cord to the outside world. Because the air inside the cabin is warm and the air outside is cold and dense, a natural pressure differential is created. The stove breathes from the outside, pulling in fresh, oxygen-rich air to feed the flames without ever touching the air you are breathing. If this intake were missing, the cabin would become a negative pressure environment. The stove, desperate for oxygen, would eventually begin to pull air down from the chimney, the very same pipe that is supposed to be carrying toxic smoke and carbon monoxide away. This is known as backdrafting. In a blizzard, when the air is thick with snow and the pressure is fluctuating wildly, a backdrafting stove is a death sentence. It will fill the cabin with carbon monoxide, a colorless, odorless gas that binds to the hemoglobin in your blood 200 times more effectively than oxygen. To prevent this, the snorkel chimney must be a masterpiece of structural engineering. A standard short chimney pipe would be buried by the snow shadow within the first 6 hours of a major storm. Once the exhaust port is covered by snow, the gas has nowhere to go. It will find the smallest leak in the stovepipe and seep into the room. Our blueprint requires a double-walled, insulated chimney stack that extends at least 48 inches above the peak of the hut's arc. This snorkel must be braced with 3 stainless steel tension cables, anchored directly to the main structural ribs. Let that sink in. The wind is hitting that 4-foot pipe with the force of a sledgehammer. Without the tension cables, the leverage of the wind would snap the chimney right off the roof, leaving a gaping hole for the snow to pour in. But with the cables, the chimney becomes a rigid extension of the hut's own skeletal frame. We use a high-wind jet cap on the top of the snorkel, a specialized aerodynamic fitting that uses the Venturi effect to actually pull smoke out of the pipe when the wind blows harder. The faster the blizzard screams over the cap, the better the stove draws. It is a system that uses the storm's own kinetic energy to ensure the safety of the occupants. Here's what everyone missed about the igloo effect. It's not just about keeping the heat in, it's about managing the dew point. When you have a 70-degree interior and a 32-degree exterior wall, the humidity in your breath will condense on the cold steel surface, creating a constant rain of condensation inside the cabin. This is why the cedar furring strips we discussed earlier are so vital. They create a 1-inch air gap between the steel and the interior wooden cladding. This gap allows the air to circulate, preventing moisture from being trapped against the metal. Without this gap, the steel would rust from the inside out, and the insulation would become a sodden, moldy mess within a single season. As we move into the 72-hour survival log, we begin to see the mechanical audit of these systems in real time. This is not a theoretical exercise. It is a time-stamped record of a structure being tested to its absolute limit by the 1978 Great Blizzard. Hour 0. The barometer is plummeting at a rate of 3 millibars per hour. This is what meteorologists call bombogenesis, a weather system that is essentially a land-based hurricane. The wind is currently gusting at 45 miles per hour, and the temperature is a steady 0 degrees Fahrenheit. Inside the Quonset hut, the sound is a low, rhythmic thrumming. The sunflowers, still visible through the windows, are beginning to dance. They are not swaying. They are vibrating with a high-frequency jitter as the wind tries to find a way through the staggered grid. Hour 6. The snow shadow has begun to manifest. Looking out the leeward windows, you can see the snow piling up in a perfect arching drift. It is not hitting the glass. It is being tucked into the low-pressure zone we created with the sunflower heads. The wind has increased to 60 miles per hour. Outside, the world has vanished into a whiteout, a state of total optical obscuration, where the ground and sky become a single, featureless void. But inside, the barometer on the wall is steady. The external combustion intake is whistling slightly, a reassuring sound that tells us the stove is breathing properly. Hour 12. The transition to total burial has begun. The snow has reached the top of the window frames on the windward side. The light in the cabin has changed from a cold winter gray to a soft, ethereal blue. This is the subnivean light. The sun's rays being filtered through 3 feet of packed snow. The sound of the wind has changed as well. The high-pitched shriek of the steel ribs has been silenced. It has been replaced by a heavy, muffled crump every time a new layer of snow settles against the shell. Hour 24. The whump factor. You are sitting at the table when a sound like a distant explosion echoes through the cabin. This is the sound of the entire snowdrift, now 6 feet deep, settling under its own massive weight. The snow is compressing, squeezing the air out of the lower layers and turning it into a structural solid. The pressure on the steel ribs is now approximately 20 pounds per square foot. Think about that for a second. On a 20-foot by 40-foot Quonset hut, that is a total load of 16,000 pounds pressing down and in. If this were a flat-roofed building, it might collapse. But the arch of the Quonset hut is one of the strongest shapes in nature. The pressure is being distributed evenly down the curve of the 19-gauge galvanized steel and into the foundation. The hut isn't struggling. It is being buttressed. The snow is now acting as a secondary structure, helping to hold the hut together against the lateral force of the wind. The temperature inside has actually risen to 75 degrees without adding more wood to the stove. We are now living in a state of thermal equilibrium. The R60 insulation of the snow has made the hut so efficient that even the body heat of the occupants is starting to contribute to the ambient temperature. Hour 36. The carbon monoxide audit. Every 4 hours, we check the digital CO detector located near the sleeping area. It reads 0 parts per million. This is the proof that the snorkel and the air intake are working in perfect harmony. Outside, the wind is still screaming at 70 miles per hour, but inside, the air is so still that a candle flame doesn't even flicker. The psychological effect of this buried stillness is profound. In a traditional house, you would hear the walls creak and the windows rattle. You would feel the ghost of the wind as it found its way through the electrical outlets. But here, inside the sunflower igloo, you are disconnected from the storm. You are in a vault. Hour 48. The midpoint of the crisis. The snow has now completely covered the hut. Even the peak of the roof is under 2 feet of white. The only thing sticking out of the drift is the snorkel chimney, which is glowing a faint, dull red in the darkness as it carries the exhaust away. We must perform a snorkel check. This involves dressing in full Arctic gear layers of wool, down, and a windproof shell and climbing out through the escape hatch built into the top of the end wall. Opening that hatch is a shock to the system. The transition from the 70-degree cabin to the minus 40-degree wind chill is like being hit by a physical wall. The wind tries to rip the hatch from your hands. You crawl out onto the surface of the snow, which is now as hard as concrete. You find the snorkel. It is clear. The jet cap is spinning at a blurring speed, and the heat of the exhaust has created a small, glassy crater in the snow around the pipe. You clear away a small buildup of rime ice frozen water vapor from the cap's vents. This is the maintenance of survival. If that ice were allowed to grow, it could choke the pipe. You retreat back into the warmth of the cabin and seal the hatch. Hour 60. The storm is beginning to lose its coherence. The wind has dropped to 40 miles per hour, but the cold is deepening. The atmospheric pressure is starting to rise, which means the bomb has passed. But this is the most dangerous time for the structure. As the wind dies down, the snow shadow stops growing and starts to settle. The weight of the snow becomes dead weight. Without the wind to provide a bit of lift over the curve of the roof, the full 16,000 pounds of the drift is resting squarely on the steel. We listen for the singing of the ribs. If the steel were beginning to fail, we would hear a series of sharp, metallic pings, the sound of bolts being sheared or corrugations buckling. But there is only silence. The 1941 engineering of the Quonset Point designers, combined with our 19th century botanical barrier, is holding firm. The living windbreak of sunflowers has done more than just trap snow. It has created a protective cradle for the building. Hour 72. The sun breaks through the clouds for the first time in 3 days. The world is a blinding, brilliant white. You open the main door, but you don't see the prairie. You see a wall of blue-white ice. You have to use a spade to cut a stairway up through the drift. As you emerge onto the surface of the snow, you look back at your home. It is gone. There is only a smooth, white mound with a single steel pipe puffing smoke into the clear blue sky. You look over at the sunflower grid. Only the very tips of the dried dinner plate heads are visible above the snow. They look like the masts of sunken ships, but they are still there, anchored deep in the frozen earth. They have been battered, stripped of their remaining leaves, and buried alive, but they did not snap. They held the snow shadow in place for 72 hours, providing the insulation that prevented the Quonset hut from becoming a galvanized tomb. This is the mechanical audit of the sunflower protocol. We did not survive because of luck. We survived because we understood the relationship between the drag coefficient of a lignified stalk and the R value of a snow crystal. We survived because we respected the lethal physics of carbon monoxide and engineered a snorkel that could withstand a gale. We survived because we turned a military surplus death trap into a biological hybrid structure. Let that sink in. In a world that relies on complex, fragile technology for survival, the most robust solution was found in the combination of 19-gauge steel and a handful of flower seeds. The numbers don't lie. The sunflower shield isn't just a garden, it's a living piece of high-performance engineering. And as the sun begins to melt the outer layers of the igloo, you realize that the most important tool you have isn't the stove or the shovel. It's the knowledge of how to work times with times the physics of the disaster, rather than against it. To move from the anecdotal to the analytical, we must subject this survival scenario to a rigorous mechanical audit, the kind of data-driven examination that separates a lucky break from a repeatable engineering protocol. In the winter of 1978, a secondary experiment was conducted on a remote stretch of the Dakotas, utilizing two identical 1941 surplus Quonset huts. We will call them Hut Alpha and Hut Beta. Hut Alpha was the control, a standard, well-maintained steel shell with modern fiberglass batt insulation placed between the ribs. Hut Beta was the sunflower hybrid, the structure we have been deconstructing, fortified by a 3-row staggered grid of Helianthus annuus and the resulting 60-inch snow shadow. The numbers don't lie, and they paint a staggering picture of thermodynamic disparity. At 0 to 100 hours, with the outside temperature holding at a steady minus 30 degrees Fahrenheit and wind speeds gusting to 65 miles per hour, both huts had their heat sources extinguished. This was the soak test, a measure of how long the interior envelope could hold its thermal energy against the relentless pressure of the high plains. Inside Hut Alpha, the descent was violent. Because the wind was allowed to hit the galvanized steel directly, the convective heat loss was catastrophic. Thermal imaging, or forward-looking infrared, revealed that Hut Alpha looked like a glowing lantern in the dark. Heat was bleeding out of every bolt head and every corrugated seam. Within 90 minutes, the internal temperature of Hut Alpha had plummeted from 70 degrees to 38 degrees. By the 3-hour mark, the interior walls were covered in a thick, crystalline rime of frost, as the thermal bridging of the steel ribs pulled the remaining heat into the night sky. For an occupant in Hut Alpha, survival would have been a matter of minutes once the wood ran out. Now, look at the data from Hut Beta. At the same 3-hour mark, the interior temperature had only dropped from 70 degrees to 66 degrees. Think about that for a second. The external environment was minus 30, yet the cabin had lost only 4 degrees of heat in 180 minutes without a single log on the fire. The FLIR camera showed Hut Beta not as a glowing lantern, but as a dark, cold mound of snow. No heat was escaping, because the R60 insulation value of the snow shadow had effectively decoupled the building from the atmosphere. The steel shell was no longer fighting the minus 40-degree wind chill. It was resting in a static 32-degree pocket of air trapped within the snow lattice. The audit revealed that Hut Beta's thermal decay rate was roughly 12 times slower than the control. But the most shocking data point came from the base plate sensor. In Hut Alpha, the concrete floor slab had dropped to 20 degrees Fahrenheit, essentially turning the floor into a giant ice block. In Hut Beta, because the sunflower-induced drift had insulated the foundation and the external soil, the floor slab remained at a steady 44 degrees. This is the igloo effect in quantified terms. By using a dead flower to manipulate the fluid dynamics of a blizzard, we converted a high-conductivity industrial material into a low-conductivity geological one. We used the storm to build a wall that the storm itself could not penetrate. This leads us to a deeper, more philosophical reflection on the nature of survival and the flaws of the industrial age. When the engineers at Quonset Point first drew the blueprints for these huts in 1941, they were thinking about logistics, mass production, and speed. They were solving a military problem: how to house 1 million men in every climate from the Sahara to the Aleutians using a single crated kit. They were masters of the hard solution, using steel and bolts to force a space into existence. But as the 1949 blizzard proved, and as the survivors of the 1978 storm confirmed, the hard solution fails when it is isolated from its environment. The steel Quonset Hut was an industrial ego trip, a building that tried to ignore the wind rather than negotiate with it. It treated the prairie as a void to be occupied rather than a force to be managed. The failure of the surplus boom wasn't a failure of the steel. It was a failure of the imagination. It was the belief that $1,000 and a wrench could buy a home that was immune to the laws of thermodynamics. The Sunflower Protocol represents a different school of thought, one that uses biological humility to fix industrial error. The sunflower does not fight the wind, it disrupts it. It does not try to stay warm, it creates the conditions for warmth to persist. By integrating a summer crop into the winter defense of a home, we are acknowledging that nature has already solved the problems of structural rigidity and fluid dynamic drag over millions of years of evolution. The lignified stalk is a better engineer than the steel mill foreman because the stalk knows how to bend without breaking and how to trap snow without collapsing. However, we must conclude with a vital, life-saving disclaimer for anyone looking to apply these principles. This is the YMYL Your Money, Your Life warning that cannot be ignored. The mechanics of the sunflower shield are precise, and any deviation can be lethal. If you attempt to insulate a Quonset hut or any airtight structure without a dedicated floor-level external combustion air intake and a snorkel chimney that terminates at least 24 inches above the drift line, you are creating a carbon monoxide trap. Modern digital CO detectors are non-negotiable. They must be rated for low-temperature operation and placed at the breathing zone roughly 18 inches off the floor. Carbon monoxide is a silent, cumulative poison. At 50 parts per million, it causes headaches. At 400 parts per million, it is life-threatening within 3 hours. In a snow-buried hut, the risk of backdrafting is nearly 100% if the snorkel is compromised. Survival is not just about staying warm. It is about the chemistry of the air you breathe. Furthermore, you must respect the structural load limits of the galvanized ribs. While the arch is strong, an imbalanced drift created by a poorly spaced sunflower grid can exert point loads that can buckle the 19-gauge steel. The 24-inch staggered spacing is not a suggestion, it is a mechanical requirement to ensure a uniform, symmetrical buttress of snow. In the end, we are left with a single, evocative image. The storm has passed, and the high plains are a sea of frozen white. A single desiccated sunflower head emerges from the top of a massive drift, its seeds long gone, its petals a memory of July. It looks fragile, a skeletal remains of a summer-long dead. But beneath that flower, shielded by the very snow it helped to capture, is a warm, breathing space where the laws of physics have been tilted in favor of life. It is a reminder that the most sophisticated survival technology on Earth isn't always something we build in a factory. Sometimes, it's something we plant in the dirt. We have taken the galvanized coffin of the 1940s and, through the study of botanical mechanics and thermodynamic snow shadows, turned it into a sanctuary of the plains. The numbers don't lie, and the stillness of the cabin in the wake of the blizzard is the ultimate proof. If you want to see more unabridged audits of the intersection between nature and engineering breakdowns that skip the fluff and focus on the hard physics of survival, then ensure you are subscribed to this channel. We are committed to documenting the forgotten mechanics of the past to secure the resilience of the future. Let that sink in. The next time you see a field of sunflowers, you aren't just looking at a crop. You're looking at a structural blueprint for the end of the world,